Hello, in this video we're going to learn how to calculate the probabilities for all the loop sizes in the 100 prisoner riddle. Now, a must-watch is Veritasium's latest video. It's titled "The Riddle That Seems Impossible Even If You Know the Answer." It's an absolutely amazing video that has a shocking solution to this problem that is definitely worth watching. And plus, he'll give a better background of the problem that I'm going to give in this one. Now, also in this video, at 9 minutes 24 seconds, he flashes a formula for calculating probability. And so I investigated that a little bit, and I have some thoughts on that, and more on that later. Now, very briefly, the synopsis of the riddle: there's 100 prisoners numbered 1 to 100. There's 100 boxes numbered 1 to 100. There are 100 pieces of paper numbered 1 to 100 randomly placed in the boxes. Each prisoner opens a box, opens 50 boxes, and then closes them to observe the number on the paper. If each prisoner finds their number, all are set free. Otherwise, all die. And that's the synopsis of the problem. Now, the loop strategy increases the probability that all prisoners survive. And I've said this a few times. It's absolutely amazing, this strategy. What it is each prisoner starts with their box of their number. So the prisoner has a number, they go to the box with that number. Now, the next box opened is based upon the current box. So if the current box has their number on the piece of paper, they're finished. They found their number, they can move on. But if it's not their number, they go to the box with that number and then open it. And if it's their number, they're finished. If not, they use that new number to go to the box with that number on it. And this strategy creates little loops of numbers within the 100 boxes. It's so amazing. And Derek does a great job of discussing the probabilities of more than 50. So the probability that a loop is 51 or more, he gives a great heuristic argument of calculating the probability of seeing that event, right? If there's a loop of 51 or more, then the prisoners, when they get in that loop, they'll use up their 50 box openings before they can see their number. And so all will die. And so knowing that probability is quite interesting. Now, this is the formula that they flash at right around 9 minutes 24 seconds. And if you were to ask me, is this formula correct? I would say, I don't know enough about the notation here to know whether it's correct or not. And now, if you were to force me to say, is it correct or not, I would say, I don't think it is. But this is not a bet, because Derek is 1 for 1 in bets, and I don't want to bet him. But the formula, it doesn't feel right. So k raised to the j factorial, it all seems like it's approaching the right thing. So it could be. So I just don't know what LT comma n minus kj time means, and this will mean more in a second. So on page 2, it's going to be pretty tedious. We're going to go through the possibilities and show you how to calculate them. So if that's your interest, this page will teach you that. If it's not, you can fast forward to page 2. We're going to go through an example of n equal 9, and we're going to find all possible loops. Okay. First, let's start at k equals 1. Now, k equals 1 means the largest loop is of size 1. So that means that it could be represented like this. So each box has their specific number. So when a prisoner goes to their box, they open it, that's their number. So that's a loop of 1. Now, in order to have a maximum of loop 1, that means every box has to have the number in it. And there's only one possible way to put the numbers in the correct boxes. Okay, so the answer is 1. There's only one possible scenario that we have a maximum loop of 1. Now another way to think about this, and it'll be strange the way I calculate it here, but it'll fit into the formula as we go down. We could, of the 9 boxes, we choose 1, and then that gets its own number. Of the 8, we choose 1, it gets its own number. 7 boxes remain, we choose 1, put its correct number in it. We do that until we get 1, choose 1. But this, I didn't have to choose them in a specific order. So this is over counting. So you have to divide by 9 factorial. And this divided by 9 factorial is 1. Okay, I'll let you do the math on that. And again, this will make more sense why we do that in a second. So k equals 2, that means the maximum loop is 2. Remember, we have 9 boxes. Okay, so my tuples here represent, we have a loop of 2, a loop of 2, a loop of 2, a loop of 2, and a loop of 1. Now this is 9 boxes, right? This is one scenario that has, a maximum of 2. We could also do this, a 2, a 2, a 2, a loop of 1, 1, 1. And this is also a case where the maximum loop size is 2. And this is a case, and this is a case. And it turns out there's only 4 cases, only 4 possibilities. But when it says a loop of 2, which 2 boxes? I mean, there's so many possibilities here that, but they all mean the same. That, there were 4 loops of 2 and a loop of 1. Okay, so now let's go through that calculations. And here, so we pick the first 2 boxes. So of the 9 boxes, we choose 2. And then there's 7 left. So of the 7 boxes, we choose 2. Of the 5 boxes, we choose 2. Of the 3 boxes, we choose 2. Now, 1, 2, 3, 4, there's 4 2s in a row. But so we could have chosen this 2, or this 2. The ordering is irrelevant. So we've actually added up too many. So we have to divide by 4 factorial. And then this one, there's 1 box, choose 1. Okay. This is the number of ways that we can have this type of loop scenario. Here, there's 9 boxes, choose 2. 7 boxes, choose 2. 5 boxes, choose 2. But since there's 3 2s in a row, we've overcounted, so we have to divide by 3 factorial. And all the other boxes have to have their specific number in them, so there's only one way for that to happen. And so this is the number of ways to have this loop scenario. Here, 9 choose 2, 7 choose 2, there's 2 in a row, so we have to divide by 2 factorial, and all the rest have their numbers correctly in the box. There's only one way to do that. Here, 9 choose 2, and then there's correct ways to do that. And so you add up these and you get 2,619. So that's the number of ways to have different loops, but the maximum be 2. Now we go to 3. Now it gets interesting. So these are the possible scenarios. We could have 3 boxes in a loop, 3 boxes in a loop, 3 boxes in a loop, for a total of 9 boxes. And this is one scenario. Or we could have a loop of 3, a loop of 3, a loop of 2, a loop of 1, and etc. And so these are all the possible loops variations where the maximum loop size is 3. Now we go through and calculate the probabilities of each of these, and this is where it gets interesting. So the first one, there's 9 boxes and we're choosing 3 of them. Now, just because we chose 3, what order can they be in? Well, there's two factorial ways that we can arrange those 3 boxes to have a loop of 3. So that's what this represents. So this number represents me picking those 3. Then there's 6 boxes left. We choose 3. Now once we choose the 3, there's 2 to the factorial ways to mix those up and still be a loop of size 3. Here, 3, choose 3, and then once those 3 boxes, we can have, there's 2 factorial ways to mix up those 3 boxes, but since we have 3 first, 3 in a row, we've overcounted, so we have to divide by 3 factorial. Now this one, so we have 9, choose 3, 2 factorial, mix them up, 6, choose 3, 2 to the factorial, mix them up. There's 2 3s in a row, so we've overcounted, we have to divide by 2 factorial. 3 left, choose 2. Now remember, when we have 2 boxes, how many ways can you mix them up and still have a loop of size 2? Well, one way, the numbers are correctly in the box and you have 2 loops of size 1. And mix the other way, you have a loop of 2. So there's only one way to mix up these 2 boxes and have a loop of 2. And then the 1 is always a 1. Now this one here, so 9, choose 3, 2 factorial ways to mix them up. 6, 3, choose 3, 2 factorial ways to mix them up. The 2 3s in a row means we've overcounted, so we have to divide by 2 factorial. And then the 1s get a 1. Here, 9, choose 3, 2 factorial, mix them up. 6, choose 2. 4, choose 2, 2, choose 2. But since there's 3 2s in a row, we've overcounted, so we have to divide by 3 factorial, right? There's 6 ways that we can mix up these 2 and still have 2, 2, 2. So we've overcounted. So 1, 2, 1, 2, we're here. So 9, choose 3, 2 factorial ways to mix them up. 6, choose 2. Oh, I'm on this one. Dang it. 9, choose 3. 2 factorial ways to mix them up. 6, choose 2. 4, choose 2. There's 2 in a row, so we have to divide by 2 factorial, and there's 1. Here, there's 9, choose 3. 2 factorials, the way to mix them up. 6, choose 2, and then 1s. 9, choose 3. 2 factorial ways to mix them up, then 1s. So there's 28,448 ways, different ways that you can have loops with a maximum of loop of 3. Now this is really the last tedious one, and then all of them are really straightforward, and that's page 3. That's what I was talking about. So when k equals 4, these are all the possible ways to have different types of loops with a maximum of 4. So we could have, 2 loops of 4, and then a loop of 1, a loop of 4, a loop of 3, a loop of 2, and etc. So now let's go through and calculate these probabilities. And this is the one that drives the method home. So we have 9 choose 4 boxes, and there's 3 factorial ways to mix up those boxes and still have a loop of size 4. And then here we have 5 boxes left, choose 4. We're going to mix those 4 boxes up, 3 factorial different ways. But since we have 4 and a 4, we've overcounted, so we have to divide by 2 factorial, and then there's a 1. 9 choose 4, 3 factorial, mix them up. 5 choose 3, there's 2 factorial ways to mix those up. 2 choose 2. Here, 9 choose 4, 3 factorial to mix. 5 choose 3, 2 factorial to mix, 1s. Oh, and etc. So then we have 1, 2, 3, 4, 1, 2, 3, 4. So 9 choose 4, 3 to mix up. 5 choose 2, 3 choose 2. There's 2 in a row, so we have to divide by 2 factorial, a 1. Here, 9 choose 4, 3 factorial, mix them up. 5 choose 2, and then 1s. Here, we just have 9 choose 4, 3 factorial ways to mix them up, and then the rest 1s. There's 61,236 different ways. Now this is what I say next is in regards to that general formula that is provided by Derek. So here, notice that there's a 9 choose 4, 3 factorial in every case, right? So that can be factored out, and that deals with that first 4, right? So really, if we factored out that 4 and then looked at this smaller tuple, these smaller tuples deal with an n of n minus 4 and k equals 4, right? And then we can find the number of tuples, that in this smaller set. That's one possibility. or we could factor out the first 4. So that's the 9 choose 4, 3 to the factorial. And then potentially sum over the next one. So the next one is a 1. So the number of ways that that can be a 1, then we sum those. And then we sum over the, the 2 in the second component. And there happens to be just 2 ways that we can have a 2 there. So we would add those probabilities. We could sum a 3 and then a 4. And so really what that I'm trying to say, so here's the general formula so far that we've just said. So we could factor out an n choose k, k to the minus 1 factorial, and then we sum over these smaller loops somehow, n minus k, k, right? That's a valid point, and it's a quick way to make the problem a little smaller, because this is always the same, and then we sum over a smaller set. So that's definitely the case. But that doesn't look like its formula. There's an additional sum out here. So if we summed over the second component, we might do something like this, where still this is that first piece out front, but then we have to add, the probabilities after each component, and we're summing over an even smaller set of loops. That's one strategy, but none of the strategies look like this. And this first piece here sort of looks like this piece, but the k raised to the j power, I'm not for sure how they get that. And then we're summing from 1 to n divided by k, the floor, so halfway up. And I don't know what we're doing there, because it says that it's the number of orders longest loop k is equal to this number. Maybe if it's less than or equal to, then this is more correct. I just don't know. Okay, so that's my thoughts on the formula there. Now let's look at when k is greater than or equal to 5. Remember, we're dealing with n equal 9. And why that becomes important is because we can't have 2 loops of size k. So if k is 5, we can't have 2 loops of 5, because that means we'd have to have 10 boxes. But we only have 9, okay? So the number of loops, you can 100% go through the strategy that we did on the previous page, where you find the number of possible loops and, etc. And it works. But here's an easier way to do it. So of the 9 boxes, we choose k of them, and then we mix them up k minus 1 factorial ways. Now, all the boxes left, there's no way that we can get a loop of size k, or 5 in this case. So we don't really care what's after that. So there's 9 minus k ways that we can mix everything up, and we'll still have the largest loop of k, because we just picked the first k. Now that's not the case when, say, n equals 4, right? Because when we pick our first 4, we just can't arbitrarily look at all the possible ways of the remaining boxes, because one of them could be a 5. And then that means we'd have a maximum loop of 5. So we have to be concerned about, all the possible loops of, k or less when we're less than that halfway point. Okay, so then when this is a combinatorics, and it becomes this, and it reduces to 9 factorial over k, which is exactly the formula that Derek got in his video. Now, an interesting research here. So further research for those interested is what's called a triangle of partition numbers to calculate how many possible loops. Now, a partition is how many ways you can break up, say, the number 5. So, 4 plus 1, 2 plus 3, 1 plus 1 plus 3. Those are called partitions. And it turns out the triangle of partition numbers is exactly tells us how many possible loop sizes we have, right? So remember, n is 9, and these add to 9, 9, 9, 9, 9, 9. So we're partitioning the number 9 with a maximum integer of 4, right? And that's what these triangle of partition numbers do. And there's a nice little recursive formula that you can use to calculate how many possible, different types of loop we have. It's exactly this number. And I'm going to let you research that more on your own. But one of the problems when n equals 100, the loops, the number of possibilities becomes so large. So when n is 100 and k equals 6, so we want the maximum loop size 6, there's 1,403, 1,043, 247. I said that wrong, 143,247 possible different loop scenarios where the maximum is 6. On 7, k equals 7, there's 407,254 different possible loops where the maximum is 7. For 8, it's 930,912. And so it really grows fast. And anyway, so that's how you do it. So, but the way we did it for 9 is exactly the way you do it for 100. Now, I may create a little R program to try to calculate these probabilities, although I have doubts that it will be able to handle 100, and I may have to go to Python or something that's faster in loops. Okay, well, that's all I have for you. I really hope Derek comments on whether that formula is correct or not. I'm so curious. Thanks for watching. I hope you enjoyed it. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.